Alrighty, so with this video I will try to solve a good number of practice problems, example problems for kinematics, two-dimensional kinematics. Previous video we went through the theory, basically stating we're using the same equations we used before for one-dimensional kinematics. It's just now, because the object is able to move in any direction at once, we have to be very careful about breaking its motion into x and y directions separately, and then using those equations either in the x direction or the y direction separately. So let's get started. Let's take a first example. All right, how about this? A bird let's say flies due north at a speed of let's say 30 meters per second. After 20 seconds, a wind begins to blow from the south, imparting an acceleration of 2 meters per second squared. If the wind lasts for 5 seconds, I want to calculate two things. First, part A, how far does the bird fly? And B, what is its final speed? Okay. So there we go. We have a nice little problem. Let's say, I'll kind of draw this one out a little bit. Here's a bird. There he is. He's currently flying with an initial velocity of 30, and he's flying to the north. Then wind starts to blow after some period of time, and it says the wind blows from the south. So that means it's blowing from south to north. That means the wind is blowing in the same direction as the motion. Okay, so there's another thing, which is an acceleration of 2, which points in the same direction as its original motion. That's important. That means it's going to speed the bird up. If instead I had said the wind blows from the north, that means it's coming from the north to the south, and that would mean the wind blows in the opposite direction of the bird's motion. If that were to be the case, the acceleration would have to be negative because it's trying to slow the bird down. Okay, so be very careful when you're reading this problem. When I give you this acceleration because of the wind, that acceleration might be positive or negative. You have to figure out, is it a positive acceleration or a negative? And of course, it's easy to figure it out. Just ask yourself the question. Does the wind blow in the same direction as the velocity or in the opposite direction? All right, now, another thing you need to be aware of when you're trying to solve problems in kinematics is the fact that all of the equations we have for kinematics are what's called constant acceleration equations. And what that means is when you want to use one of these equations, it must be true that the acceleration does not change. It might be 0 It might be some number, but you can't have a changing acceleration. Well, if you look at this problem, note that the acceleration changes. At first, the bird's flying with no wind, so there's no acceleration. But then, all of a sudden, after some period of time, all of a sudden the wind starts to blow and you do have an acceleration. So what that means is, because the acceleration changes, we must split the problem into different parts. That is to say, one part when the wind isn't blowing, the acceleration is 0, and then a second part when the wind does blow and the acceleration is 2. We solve the problem with no acceleration, get an answer. We solve the problem with the acceleration, get an answer. And then we add those two answers together to get the total answer. It makes sense, right? If you want to know how far the bird flies, first calculate how far does it fly before the wind starts. Let's say it goes 100 meters. Then you say, now that the wind's blowing, how much further does it go? Well, maybe it goes an extra 50 meters. So all in all, the total distance that the bird flies is 100 plus 50. That's basically what we're going to try to do here. So let's do it. Part A. I want to know the total distance the bird flies. Because the acceleration changes, I have to do this in two parts. So the first part says x1, I'll call it. That's the distance that the bird flies before the wind. What equation can I use? Basically, what you want to do, have your equation sheet so you can look at the equations, because I don't necessarily have enough room to write them every single time. But if you look at your kinematics equations, and you ask yourself, which equation can I use, given that I'm looking for a distance, I'm given an initial velocity, I'm given a time, and an acceleration. Obviously, the equation I'm going to use is x equals v naught t plus 1/2 at squared. Now, I'm looking for x1, so I'll put a little 1 there, just so I remember. This is the distance that the bird is flying before the wind. All right, so let's plug our numbers in. The initial velocity of the bird is 30 to the north, so I'll call the north as positive. So 30. For how long does he fly? 20 seconds. Remember, for the time, I don't mean the total time. I only mean the time during which this acceleration is true. For this part, x1, it's when there's no wind. So the time I'm plugging in is just the first 20 seconds. Then I have plus 1/2. The acceleration when there's no wind is 0, times t squared, 20 squared. So this becomes 30 times 20, which is 600 meters. So what we just found out is, how far does the bird fly before the wind starts to blow? The bird flies 600 meters. All right, well, what about part 2? Now that the wind starts to blow, I want to know how much further does he go. So again, x2 this time is v naught t plus 1/2 at squared. What's the initial velocity? Well, let's think. The bird was flying, there was no acceleration, and he was originally moving at 30, so by the time the wind just starts to blow, he's still moving at 30. That hasn't changed. So his initial velocity is still 30. The time, remember, the time I plug in here is the time during which the wind is blowing, because that's the acceleration I'm talking about. So for this part, the wind only blows for 5 seconds. So the time is 5. Plus 1/2. The acceleration, the wind blows giving an acceleration of 2. Again, the wind is coming from the south, pushing towards the north. The bird is flying to the north. They're in the same direction, so this is positive. So positive 2. And again, the time is 5. So this I want to plug into my calculator, and I get 150 plus 25 is 175 meters. All right, well, now to answer part A, how far does the bird fly? Before the wind starts, he flies 600 meters, then the wind starts to blow, so he goes another 175 meters, so the total distance x is 775 meters. There's my answer, the total distance flown. Okay, now what about part B? Part B wants me to find the final speed, so I'm looking for final velocity. So I would look at my equations. Obviously, the first equation, x is v naught t, that one, doesn't have final velocity in it, so I'm not going to use that one. What can I use? The second equation that has final velocity, it has an initial velocity, which I know. It has acceleration, which I know, and it has distance, which I know. So I could use the second equation. Could I use the third equation? Third equation, acceleration is final minus initial velocity over time. Yes, I know the acceleration, I know the time, I know the initial velocity. So I could use either one. Let us say I want to use the third equation. Let's say I use this one. Acceleration is final minus initial over time. I want to solve this for final velocity. So first step, bring the t to the other side. So at is final minus initial. And then, of course, get the final by itself. So I add initial over. I have final velocity is initial velocity plus a times t. Plugging in my numbers. Initial velocity, before the wind started blowing, the bird was originally flying at 30. So 30. Plus the acceleration. Now that the wind is blowing, what acceleration does the wind give? 2 meters per second in the same direction. So he's positive 2. And then the time, again, don't think total time. This equation only makes sense if the time is the same time as the acceleration, right? Because if not, if I try to put total time, that would imply that the bird feels this acceleration the whole time it's flying. But of course we know it's not. It's only feeling the acceleration while the wind blows, and the wind only blows for 5 seconds. Thus, the time I plug in is 5. And there we go. Add these together. 30 plus 10 is 40 meters per second. And there you go. That's how you want to look over how to do these types of problems. This one or one similar with an airplane or whatever, if you have a problem where at some point the acceleration changes, the big hint is to say, okay, I'm going to be splitting this problem into 2 pieces. The first piece is the original acceleration. The second piece is the new acceleration after it changes. And you solve it like we did here. In this case, solving for the total distance, I had to get the distance before the wind and then the distance after the wind and add them together. And for the final velocity, of course, any other problem you have to do when you're plugging these equations in, just remember you have to be careful when you're plugging in time or distance that you're only plugging in the amount of time or the amount of distance for the acceleration you're talking about. Here we had a problem. The bird flew a certain amount, then the wind started blowing, so the time while the wind blows is only that 5 seconds, not the full 25 seconds. Be very careful about that. All right, let's try another example. This is a big one. This is a cannonball question. Here we have a cannon. The cannon shoots a cannonball with an initial velocity of 20. The cannon shoots the cannonball at 60 degrees, let's say. And of course the cannonball is going to go up and back down again. What do I want to calculate? I want to know, part A, let's say, what is the maximum height reached by the cannonball? Part B, maybe I want to know the time of flight. And then part C, the range. How far horizontally does a cannonball go? This question is the perfect generic kinematics problem because it teaches you how to think about the different directions separately. It teaches you how to find components, and it teaches you how to use the equations correctly, which equations to use for what. So this is a very, very important example. First thing to know is for any problem you ever do, if you see that there's some piece of data in the problem that's at an angle, you most likely want to first break that angle up into its components. So we have an initial velocity, but that initial velocity is at some angle that's not good. So I'm going to break it up and get an initial velocity in the x direction and an initial velocity in the y direction. Because since the equations I'm using are vector equations, I know I can only do stuff if it's all in the same direction. Things that are in angles are bad. So break the angle thing up into x and y components. So we look at our little cannon, make a little right triangle here. And I say, okay, here's the x side, here's the y side. So if I want the x component of this initial velocity, that side is a side adjacent to the angle. And we remember from SOHCAHTOA that adjacent goes with cosine. So initial velocity x component is the 20 times cosine of the angle. And plugging that into the calculator, you get 10. What about the y? Same thing. The y side, that side is opposite to the angle. SOHCAHTOA says opposite goes with sine. So it's 20 times the sine of 60, which is 17.32. Now that that's done, all the information in this problem is going to be in x and y directions. Now I can start. Let's look at the maximum height. So just as before, the equations we're allowed to use, we have x equals v naught t plus 1/2 at squared. Vf squared is v naught squared plus 2ax. And acceleration is final minus initial velocity over time. And I have to choose one of these equations to calculate the maximum height reached by my ball. So, what do I know? Well, first of all, when I'm asking for maximum height, what I'm asking for is the distance here from ground level up to the top. Call it h, let's say. The very highest level the ball reaches. Well, first thing I know is that's a distance, right? The maximum height is the distance from the ground to the top of its path. Not only do I know it's a distance, but I know it's a distance in the y direction. So whatever equation I'm about to use, I must use the y direction stuff to calculate it. I can't use any x direction information here because I'm looking for a y distance. So I can only use y information. Well, which equation can I use to calculate a distance? Let's look at the first equation. All right, distance is v naught t plus 1/2 at squared. So it's got distance. That's good. Do I have all the information? Well, let's see. I need an initial velocity, of course, in the y direction. And I know it. It's 17.32. I just calculated it. I also need a time. So that means I need to know how long does it take to get to the maximum height. Do I know that? No, I don't know that. So that means I can't use the first equation. I don't have enough information. So let's move on to the second. For the second equation, do I have a distance? Yep, at the end there's x. So I can calculate distance. Do I have all the information? Let's see, I need an acceleration. Do I know a y acceleration? Yes, it's gravity. Gravity is the thing pulling the ball down. That's the thing giving it an acceleration. So I know that. That's negative 9.8. I need initial velocity, also y direction. Again, I know that. I just calculated it. But then I also need to know final velocity in the y direction. Do I know that? And here it's tempting to say no. I don't know the final velocity because it's not given in the problem and I don't have it written out. But here it's kind of tricky. We do know the final velocity of this ball in the y direction. Think about it. As the ball goes up into the air and reaches the top, looking purely in the y direction, I want to know how fast is the ball moving at that point. Well, let's think about it like this. I'm going to assume the final velocity of the ball at that top point must be 0. Why must it be 0? Well, okay, if it's not 0, that would imply it still has a positive velocity upwards. So that would imply it's still moving up. But I'm specifically asking for the velocity at maximum height. That means it's not going up anymore. It's as high up as it could possibly go. So the only way the ball could have reached the maximum height is if the y direction velocity got to 0. And then after, of course, it's going to start falling again. But right at the top, in the y direction, the ball must have stopped moving. Just before then, it's moving up. Just after then, it's moving back down. But at the tip top, it's not moving at all. Now, of course, in the x direction, it's still moving. But we don't care about x stuff. We're only looking at y. So this is a big tip. When you're looking at the maximum height, the final velocity of the ball in the y direction is always 0. Because again, if it weren't 0, it must still be moving up. And thus it's not yet at the maximum height. So, yes, we do know the velocity, the final velocity in the y direction at the maximum height. It's 0. So good. I could use vf squared is v naught squared plus 2ax. Plugging our numbers in, again, I'm going to put a little note here. I'm looking in the y direction, just so we remember. Final velocity in the y direction, that's 0. Initial velocity in the y direction, 17.32 squared, and that's upwards. Plus 2 times the acceleration. Well, the acceleration in the y direction is gravity. Gravity is negative, or downwards, 9.8. And in x, that's exactly what I want to calculate. What is this distance x? How high does the ball go? And now here's my equation. All I have to do is rearrange it, manipulate it using algebra, and calculate x. So if I want to get x by itself, first thing I do is bring the 17.32 squared to the left. So he becomes negative 17.32 squared equals 2 times negative 9.8 is negative 19.6 times x. All right, I want to get x by itself, so divide over the negative 19.x. X equals, the negatives cancel, and you have 17.32 squared over 19.6. We plug this in our calculator. 17.32 squared over 19, let's see, 15.3 meters. So there we go. How high will this cannonball rise? 15.3 meters. All right, so part A is done. Now I want to look at part B. Part B says, what's the total time of flight? Okay, which equation can I use? Well, I definitely can't use the second equation because that equation doesn't have time in it. So it must either be part A, the first equation, or the third equation. Let's look at the first equation. First equation says x equals v naught t plus 1/2 at squared. Can I do this in the x direction? Well, let's see. I'm looking for t. There is a t in the equation. That's good. Do I have all the x information? I need an acceleration in the x direction. Do I know that? I do know that. Nothing is pushing the ball in the x direction. There's no wind or anything. So the x directional acceleration is just 0. So that's fine. I need to know v naught. Do I know the initial velocity in the x direction? Yep, it's 10. I calculated that at the beginning. Do I know x? Do I know the x distance? How far the ball will go in the x direction? I don't know that. This x I calculated in part A, remember, is the y distance. How far will it go in the y direction? Here I'm looking for how far will it go in the x. I don't know that. So I can't use the first equation in the x direction. However, can I use it in the y direction? So let's go back through it. I'm looking for t. That's fine. The acceleration, do I know the acceleration in the y direction? I do. That's gravity. Do I know the initial velocity in the y direction? Yep, 17.32. And do I know the distance in the y direction? I do. In fact, I know two different distances. The first distance I know is what I calculated in part A. That distance is the maximum height. So if I were to use that distance in this equation and calculate the time, that would tell me how long does it take to get from the beginning to the maximum height. But that's not really what I'm looking for. I'm looking for the total time of flight. That is, the total time it takes to go from the beginning all the way to when it lands at the end. I need the total time. So do I know that distance in the y direction? Well, yeah, I do. That's easy. Notice the cannonball is shot from the ground and it lands on the ground. So what's the total difference in the height of the cannonball from beginning to end? It started at ground level, ends at ground level. There's no change in the height. So that means in the y direction, the ball went 0 meters. Obviously, in the x direction, it moved, but in the y direction, it didn't move. So all I need to know is that the distance in the y direction from beginning to end is 0. This would be different if, let's say, I shot the ball off a cliff and the ball landed on the ground below the cliff. Then it would have dropped a certain amount. So maybe negative 10 meters. Or if I'm a golfer and I hit a golf ball up to a raised green, then the y distance might be positive 2 meters or something. But here, the cannonball was shot from the ground and it lands back at the ground again. So the total change in height is 0. Thus, looking in the y direction again, using the equation x equals v naught t plus 1/2 at squared. I want to solve this for time. What do I know? Well, the y distance from beginning to end is 0. Initial velocity in the y direction, 17.32 times t plus 1/2. The acceleration is downwards, so negative 9.8 times t squared. And now this is the equation I need to solve for t. Well, at first it kind of looks quadratic. There's a t squared in it. But remember, a quadratic equation needs a t squared, a t, and a constant term. This doesn't have a constant term. So really all I have to do, if I rewrite this, 1/2 of negative 9.8 is negative 4.9 t squared plus 17.32 times t equals 0. All I did was rewrite it. All I have to do, notice there's a t on both terms. Let's factor out a t. So I get t times negative 4.9 times t plus 17.32 equals 0. Right? I took one of the t's from the first term, and I took the t from the second term, pulled it outside, and everything that's left is in the parentheses. And now all I have to do is figure out how do I solve an equation like this. And we discussed this at the beginning of the semester with math. If you have something that looks like a times b equals 0, this implies that a is 0 or b is 0. Thus, either t is 0 or this whole thing is equal to 0. Let's think about what t equal to 0 means. T equal to 0 means the ball reaches the ground level after 0 seconds. Well, obviously, all that means is you haven't shot it yet. So that's not the answer I'm looking for. If I want the time of flight, it can't be 0. It means I didn't do anything. So let's look at the other one. Negative 4.9 times t plus 17.32 equals 0. I want to solve this for t, so I bring the 17.32 over. Negative 4.9t equals negative 17.32. Divide over and get t is negative 17.32 over negative 4.9, which tells me 17.32 over 4.9 is 3.53 seconds. So what's the time of flight? It takes 3.53 seconds to go from when it's shot back down to the ground again. All right, one more to go, part C. Part C says, what's the range? Well, of course, we need to understand what range means. Range means the horizontal distance traveled. So, what is it I'm looking for? I'm looking for distance in the x direction. So let's look at our equations. Can I use the first equation to calculate the distance in the x direction? Well, first I need to know t. Well, first, does it have an x in it? Yes, it does. X is good. Next, I need a t. Do I know the time it takes for it to go the full distance? Yes, that's what I just calculated in part B. Do I know the acceleration in the x direction? Yes, it's 0. There is no acceleration in x. Do I know the initial velocity in the x direction? Yes, I calculated that at the beginning. That's 10. So I've got everything I need. Looking in the x direction, I'm using the equation x equals v naught t plus 1/2 at squared. And now I just plug my numbers in. Initial velocity x, 10. T, 3.53. Plus 1/2, acceleration in x, 0. And t squared, 3.53 squared. But all that's 0 because it's 0. So you get 35.3 meters. And that's the range. That's how far the cannonball will travel. So that's how you attack one of these cannonball questions. You start with, if the cannonball is shot at an angle, break up the initial velocity in x and y components. That's this stuff over here. Very critical. From there, what are my equations? What am I looking for? In this case, I'm looking for maximum height. That means I'm looking for a y distance. And then I ask which equation allows me to calculate it. I could not use the first equation because that required me to have time. And I didn't know the time yet. The third equation doesn't even have x in it, distance, so I couldn't use him either. So I knew inevitably I had to use the second equation in the y direction. The only trick was this final velocity bit. Here, for the first time, we're seeing the trick, and it works every time. If you're looking at maximum height, then the y velocity must be 0. Because if it's not 0, then it must still be moving up. And so it wouldn't be at the maximum height. So good. I use the second equation. Final velocity is 0. Initial velocity for y. Gravity is there, pulling downward, so he's negative. And I solve for x, I get a distance. That's how high the cannonball will go in the y direction, from ground level. And now part B asks me to find the time of flight. Well, this I can either use x or y. I don't know yet. I do know I need to know the time, so I can't use the second equation. So we looked at the first equation and said, okay, I'm going to use the first equation either in x or in y. I looked in x first, and I found I cannot use it in x because I didn't know the distance the ball travels in x. So I must use it in y. And I said, okay, well, what distance do I look at? If I use the distance I just calculated, the maximum height, that answer would tell me how long does it take to reach that point, which is the maximum height. But that's not the total time. That's only half the time. So the first thing you could do is use this maximum height for your distance, calculate the time, and then multiply by 2. But that's harder. The easier way is to note that because the ball lands at the same height as it started, I'm not on a cliff or something like that, then the total y distance travel must be 0. So I plug my numbers in. I have an equation for t. It's got a t squared in it, so it's just a little bit more complicated. But all you do is factor the t out. Solve, you get 2 answers. The first answer is t equals 0. But we know that can't be the right answer. That just means you haven't shot the ball yet. The other answer, 3.53, that must be the total time of flight. Finally, for part C, for the range, we say, well, range means a horizontal distance, so I'm looking for a distance in the x direction. I can't use the last equation because it doesn't have distance in it. The first equation, do I have everything? I know the time. Acceleration in x is always 0. Initial velocity in x, I know. So I could use that. I plug everything in. Nice easy equation. And I have the total range. How far will the cannonball go? That's basically how you want to attack these problems. This is a very critical problem to be able to do, so practice it. Practice it where the cannon starts at the top of a cliff, and it falls down to the ground. So maybe the cliff starts 10 meters high, and do the same type of process, and you'll see how it changes. Let's see. The video is 40 minutes. It's kind of long, so I think I'll end it here. I hope these 2 problems help you, especially with the homework questions and the like, to kind of get a good grasp of the methodology behind these problems, you're going to find when you look at the homework problems and the practice problems, there's all sorts of different ones on there. Some are similar to these, but others are different. But as you practice, you're going to find that the way you go about solving the problems is always the same. You may have to use different equations. You may have to ask slightly different questions to yourself. But at the end of the day, all problems are solved like this. You can draw a little picture to help you visualize what's going on, have your equations in front of you, and just go one by one. Do I have anything that's at an angle? If I do, break it up into x and y components first, just to have the information there to use. Number 2, when I use these equations, they must always either be totally in x or totally in y. So don't mix and match information. If I'm looking in the x direction, I can't have the acceleration as gravity. Gravity is only y. In fact, except for very special questions, the acceleration in x is almost always 0, at least for these types of problems. Also, figuring out which question to use is just a matter of asking questions to yourself. Which equation? Say, okay, I want a time. Which equation can I use? The first equation has t, that's good. Do I know information? Well, that depends. Am I looking in x or am I looking in y? So you start looking in x first. Do you have all the x information? If not, then look in y. Do I have all the y information? If again not, move to the next equation. However, if you do happen to have all the information in one of the directions, then use it. Inevitably, you will always be down to one of these 3 equations. And it's always, almost always, one of the first 2 you will find. So, practice the heck out of these. Look at the practice problems on Canvas. Look over the solutions when you get stuck. But definitely be used to sitting with a blank sheet of paper and doing it all yourself. When we get to the first test, you're going to find that if every time you did problems, you were always watching the solutions at the same time, that's not good enough to help you there. You have to be used to only having a formula sheet and a blank sheet of paper in front of you, because that's what test conditions are like. If you can't solve the problem with a blank sheet of paper, then you don't know it well enough yet. You can't have the crutch of being able to constantly look at the solutions to help you out. It's fine towards the beginning if you're unsure, but don't use the solutions to help you solve the problem and then think, oh, I know it now because I finished. Well, no. You have to go back and try to do it yourself a few times as well. But with enough practice, this stuff will become second nature, believe me. The only reason I can do these problems without looking is because I've practiced hundreds and hundreds of problems over the years. When I very first class started physics, I had trouble with it too. We had to memorize our equations, so that made it even worse. But it wasn't necessarily completely straightforward and second nature to me. I had to practice it. I went home, did problems over and over and over, till I knew when I get a problem, even if it's a problem I hadn't seen before, I know I can think my way through it. I can ask the questions necessary to guide my thinking to figure out which equations I can use, how to plug in the numbers, and how to solve the equations. And you need to get to that point too, and the only way to do it is, unfortunately, to force yourself to sit down at a table or an iPad or something like that and physically work the problems out. And I promise you, if you work these problems out, the homework and the practice problems, the test questions are going to look very, very similar. So the faster you start working them and learning them, the more likely you are to make 100 on these tests. Anyway, that's enough of a rant for now. I hope this was helpful. As always, if you have more questions as you're working these problems yourself, feel free to email me, send pictures of your work, whatever you'd like, and I will either respond, with words, or write something out and take a picture of it myself and send it back, however it needs to be done. Just as long as you're understanding, you're keeping up to date, things are going to go well. So until next time.